Hey class, welcome back to Electromagnetics. We're going to continue our look at antennas and some basic principles of that. And so today I want to introduce the concept of antenna arrays. We'll do a quick historical background. This one's not so applicable to electromagnetics, although he is remotely, and I'll explain that in a minute. But he's also just one of my favorite historical mathematicians. Really amazing story. So let's look at this person. Educated, education. He was mysteriously self-taught, and there's still a lot unknown about this and the way he came up with things. The only work that's notable was that he briefly worked at Cambridge University. This is a picture of this gentleman. Perhaps this is familiar to you. And this is Ramanujan. So Ramanujan has a pretty incredible story. There was a movie I made about him recently. I think it's called The Man Who Knew Infinity. And his interaction with some of the great mathematicians at Cambridge University. He started in India. Best we can tell, he had no formal teaching. He taught himself and came up with some pretty amazing things. So what are some of the notable things? Well, just like I said, he offered numerous claims and theories with almost no justification that seems to be accurate, at least the ones that they figured out, they are accurate. And the crazy thing, or the striking thing, is that it appeared that he was able to offer these complicated solutions merely from intuition, that he had an intuition or an insight into this, that some of these genius mathematicians took them years to figure out where it came from or how it made sense. So let's look at some examples of that. So the first one, example of his work, is that he offered a new approximation for the value of pi. And this is the way that he expressed it. Of course, this is 1 over pi, so whatever the solution we calculate on the right, we can, of course, just invert it and get pi. Well, the amazing thing about this equation is that it converges to pi extraordinarily and exponentially fast. And so it was like orders of magnitudes more accurate than anything they had at the time. And he never really gave any explanation for it. He just presented it, and then no one's really been able to figure out what was his basis for coming up with this, that he just had an insight into the way the function pi behaved. And this thing is so accurate and it works so well that this equation, even today, forms the basis for some of the fastest algorithms used to calculate pi. So you can see from the dates on his lifespan, the 1920s, it's amazing that someone 100 years ago came up with something that's still about the best we've come up with to calculate pi. And again, we still are not exactly sure how he came up with it. It's just very mysterious. I want to show you one more thing that was in one of his notebooks. Now, Euler and Riemann both kind of approached this problem as well, but Ramanujan kind of confirmed it, and so there's still a lot of controversy around this, but I think it's still a fun thing to kind of show you that sometimes we don't understand things as well as we think we do. And so this has to do with what the sum of all the natural numbers are. That is, if we just take 1 plus 2 plus 3 plus 4, so on and so on to infinity, what would that equal? Now, of course, we can express that as this summation, n equals 1 to infinity of n. And what is that equal to? Well, intuitively, we would think that has to equal to infinity, right? Well, Ramanujan said, not so fast. This is what Ramanujan, a simplified version of what he said. Let's consider some other series first. Let's call series 1 just going to be 1 minus 1 plus 1 minus 1 plus 1 forever. First question is, what is that equal to? The second summation is going to be 1 minus 2 plus 3 minus 4 plus 5, so on and so forth forever. What is that equal to? And then finally, we're going to have the one we're interested in, 1 plus 2 plus 3 plus 4 plus 5. So let's see what Ramanujan did with this. So first, Ramanujan took the first series and he said, well, if we were to take the definition or summation of n equals 0 to infinity of x to the n, if we set x equal to minus 1, well, then this becomes 1 over 1 minus x for x equal to minus 1. And we learned this in calculus, right? That for that these series converge to these certain things. So by definition, if you go back and look at your calculus, this is what this will come up with. So when you plug then this x equals minus 1 into this equation, oddly, we get that this comes to 1/2. And so some people tried to justify that to say, okay, this thing alternates between 1 minus 1, 1 minus 1, 1, I mean 1 and 0, 1 and 0, excuse me, 1 and 0, so the average would be 1/2. So that one, even though that's not exactly true, we can almost kind of see that. Well, it gets much stranger. So now Ramanujan noticed that if we take the second series, 1 minus 2 plus 3 minus 4 plus 5, that this is equal to, or can be expressed as, n equals 0 to infinity of n times n minus 1, which of course is just the derivative. If you look at this, this is the first derivative of this. And let's still keep x equal to minus 1. Well, again, we know from calculus, we've derived expressions for these series, and in this case, we get 1 over 1 minus x squared. So again, if we let x equal to minus 1, now we get a summation of 1/4. Well, now this is starting to look a little strange. How can that be equal to 1/4? There's no fractions in this whatsoever. Well, let's just hold on. We've got more. Much more. Now let's take it to the next level. So now we've got our first sum supposedly equal to 1/2. That's what the calculus tells us. Summation, second one, this one equals 1/4. Still, these are a little troubling, but we want to continue on. Now we notice that if we take our original series and we subtract the second one from it, what do we get? Well, here's our original series, 1 plus 2 plus 3 plus 4 plus 5. Now we subtract the second series, 1 minus 2 plus 3 minus 4 plus 5. We see now that this will be 1 minus 1, so that would be 0. This will be 2 minus a negative 2, that would be 4. 3 minus 3 is 0. 4 minus a negative 4 is 8, so on and so forth. So this is what this comes out to. Well, we realize that, oh, well, that's the same as our original series, just times 4. So now that's kind of strange as well. So we're going to start out with the original series. We're going to subtract something from it, and we get 4 times that. Hold on, it gets even stranger. So now we realize that we can set up this equation to say, okay, s minus s2. Well, we know that s2 is 1/4, right? So we can just say, instead of s minus s2, we'll say s minus 1/4. Well, we know that this is equal to, we've just calculated here, 4s. So now we have s minus 1 over 4 is equal to 4s. This tells us then, if we solve for s, that s is equal to negative 1/12. But wait a minute, what is s? S is our original series. That's the sum of all the natural numbers. So Ramanujan showed that the sum of all the natural numbers is equal to negative 1/12. This bothers me greatly on many levels. Number one, that it's a fraction. How in the world did you get it to be a fraction? But even more than that, how in the world does the addition of all the positive integers give me a negative number? So not only is it a fraction, it's a negative fraction. Well, there's many people that brush this off as nonsense. They say that it's violated the rules of convergence. And some people still argue about that. And, there's videos on YouTube about it, and there's, articles written about it. And so many people just disregard it as some kind of anomaly. The only problem is there's been some research done in what's called quantum electromagnetics. Now, I'm not even going to try to start to tell you what that is. That's way beyond the scope of this course. But as they were solving problems with quantum electromagnetics, trying to get it to describe what they were observing at the quantum level, one of the equations that they had came up with this original series of the sum of all the natural numbers. And so they thought to themselves, oh, well, our model must be crazy or must not be right, because that means the equation blows up. Well, one of the researchers said, hey, I remember from my my number theory class that there are some theories that say that that's equal to negative 112. So they said, well, let's just try it. So they stuck the negative 112 in for that summation of all the natural numbers in their equation, and guess what? It appears to work. So something really strange is going on there, at least at the quantum level. So this is fascinating to me. I'm very interested in this type of stuff in number theory and trying to figure this out. I think these are sometimes little nuggets the Lord puts in our daily lives in mathematics to kind of let us know, hey, you don't really maybe know as much as you think you know, and maybe to keep us humble. I don't know, just an interesting thing. Ramanujan actually came up with many amazing things like this and equations like for pi that still nobody knows where they came from. So anyway, moving on. So we want to continue our look at antenna basics. And so we're up to the fourth lecture where we want to talk about antenna arrays. So up to this point, we've only looked at single antennas, the Hertzian and the half-wave dipole. But we now want to see what happens when we utilize multiple antennas. This is very common today and actually is used quite a bit. And this is referred to as an antenna array. So this is a common application when transmitting or radiating electromagnetic waves, in that you strategically can space the antennas apart and strategically control the phase shift or the phase difference between the sources of the antennas. When you do this, you almost have complete control and can create any radiation pattern that you want. You can customize it, and there's a lot of theory in this. I mean, you can take a whole course on this. It's actually pretty interesting. So this can be extremely useful when trying to broadcast light to only a specific direction, or if you're trying to hit one source in a very narrow band far away, and you don't want to broadcast it in all directions. So let's look at how this works. So to start, let's think of just two antennas. We're going to say there are two Hertzian dipoles, and so we're going to place them D apart. So from the origin, it'd be D over 2 this way, D over 2 this way. We'll feed them with two different current sources, I1 and I2. And we're going to look at an arbitrary point out here. So again, we'll have R from the center between the two antennas, R1 and R2 are from each separate antennas. And we're just going to look at the E field. So when we say we're just looking at the E field, we're going to have this transverse field, right, from the direction away from the center. So this is the resultant, but we have these separate contributors from each antenna. So, and also we have these thetas that are made with the antennas and then from the origin itself, and then this phi term, which is the opposite angle made with the x-axis. So you might need to refer back to this once we do the setup, but it shouldn't be too complicated. So first thing we want to do is control our current sources. So we'll have I1 feeding antenna 1 and I2 feeding antenna 2, and they'll be exactly the same except for we're going to have this polar opposite on the phases there. So I'll have the first one is plus alpha over 2 and the second one is minus alpha over 2. So again, we're just considering this arbitrary point P, and we want to compute the resultant E field from this antenna array. Well, if we use the analysis from before, and I don't want to go through all the math because we don't have time to do that. Just want to introduce this concept to you. So you can take my word for it that the contribution from the first antenna will be E1, and we get this expression, and the contribution from the second antenna, E2, we get this expression where the main difference is, of course, we've got the theta 1, theta 2, R1, R2, but it's the biggest difference is the plus alpha over 2 minus alpha over 2. And here again, we're using all the variables that we defined in the figure shown earlier. Well, for now, we're going to consider just the far field, right? So we're assuming that the radius or the distance from the array is much, much greater than the space between the antenna arrays. So when we do this, we can make some interesting assumptions, at least relative to our point, which is pretty far away, and that is that theta 1 is about equal to theta 2, which is basically equal to theta. R1, R2 are basically equal to R, and these directions are all basically the same. The differences in them are minuscule, and they don't make that much difference. So this assumption for the R term is adequate in the amplitude portion of our equation, but it doesn't work in the phase portion of our equation. So in the phase part, we still need to keep track of the different R values. And so the R1 is basically equal to R minus D over 2 cosine phi, and then R2 is basically equal to R plus D over 2 cosine phi. So we're going to take these approximations and see if we can simplify our equations a little bit. So using these assumptions, we can now apply superposition at our point, and when we do, we get a resultant expression for the total field. So we should expect that E will be equal to E1 plus E2. So when we plug these values in and the assumptions that we made, this is the resultant equation we get for the field. So when we do this, we should be able to recognize that this equation is almost identical to the E field equation for just a single Hertzian dipole, with one major exception. And that is this factor here, this 2 out here, and then this cosine. So this 2 cosine beta d cosine psi plus alpha over 2. Well, this factor right here is what we commonly refer to as the array factor. And this is what gives us our control over these array patterns, as we'll look at here. So we now observe that the resultant field pattern, this is the pattern that we observe at all points from the array. And it's given by the product of sine theta, which is basically the unit pattern, or the pattern of just a dipole, multiplied by this group pattern, which is this cosine factor we saw before. So we have two different things going on. We can have the pattern associated with whatever type of antenna, which in this case we're using the Hertzian dipole. You can put other kind of antennas there if you want, but it's going to give you a different unit pattern. And then we've got our group pattern, which this is determined by how far apart we may set the antennas and the phase difference between the sources fed to them. So let's look at this further. So with this understanding of the relationships in these new terms, unit pattern, group pattern, and resultant pattern, we now want to look at some special cases that are frequently used in antenna array design. So let's see how this works. And what's going to vary here is, like I just said, again, we're using these Hertzian dipoles, and we're going to vary the distance between the antennas. And I'll show you what the definition is for each case. And we're going to control the phase shift between them. That's between the two current sources feeding the antennas. Again, I'll be sure and define those. So let's look at these cases. So for case 1, this is what's commonly known as a broadside pattern. And so in this case, the separation between the two antennas is lambda over 2. And the phase difference is 0. There is no phase difference. And so for this case, the group pattern is this right here, which is just basically, since it's an even function, you don't have to have the absolute value signs there. And beta lambda over 4 reduces to pi over 2 because of d equal to lambda over 2. And so if we were to plug in some values for psi, we get the magnitude of the group. So at 0 degrees it should be 0, at 45 it's 0.4, at 90 degrees it's 1. And so if we were to plot some of these and get some more points, this is basically what this pattern is going to look like. And so here's our two antennas. And so again, we see it's psi equals 0, and so that's in this direction here. We see there is no field pattern radiated there. At 90 degrees, which is straight up, we see it's maximized at 1. And then as we start to rotate around here, like to 135 degrees, we still have some pattern radiated in there, but it's less than half of what we would get here, so on and so forth. So this is what's known as a broadside pattern. So, if you had a target out here, or maybe in the back as well, then this might be what you want to use and not have it be intercepted over on the sides. So the next one we want to look at, this is case number 2. This is what we would call an end-fire pattern. And so for here, we're still got lambda over 2, but now we're going to vary the phase difference between the sources feeding each antenna by 180 degrees, or by pi. And so in this case, we plug in the values up here and solve for it. This is going to give us sine pi over 2 cosine phi. And again, we can plug in the numbers here. If we were to do that and plot them out, this is what that would look like. So it's similar to the broadside pattern. Now, instead of going up and down in between the antennas, now it goes out to each side of the antenna. So That's why we really call it an end fire. So another commonly used array pattern there. So case number 3 is another form of an end fire pattern. So again, here we're reducing the distance between the antennas to be lambda over 4. And now the phase difference between the two sources is negative pi over 2, or negative 90 degrees. So now if we look at the group pattern for this case, plug in the values, we get this cosine, complicated looking cosine function here. We could plot the points out, and when we do, this is what this guy looks like. And so here you see around this antenna there's almost nothing. So the way that the phases all match up, they all cancel each other out, and here they add together. And so I've seen this actually used for applications where you're just wanting to broadcast in this direction. You could even use this with radio antennas. Say like you were on the coast and you didn't necessarily want to broadcast out over the water, but you want to make sure and shoot it all, but most of your power or radiation back inland. So you could use an end-fire pattern such as this. And so the last one is just an arbitrary one, case 4. What would happen if we put the antennas lambda apart, one wavelength apart, and there was no phase difference between them? Well, in this case, we get the cosine of pi cosine psi. Here's some representative points. Again, you can put a lot more than that if you want. And in this case, you would get something like this. So now we're kind of projecting in all different directions. And so this doesn't really have a name associated with it like end-fire or broadside. But you can see you can start to create any kind of pattern you want here. And there's a lot of people that make a career out of doing this. So what about the resultant pattern? Those were all just group patterns, right? That's just part of the equation. We now want to use the unit pattern in relation to this with the group pattern to get us some resultant patterns. So what does this look like? Well, here's the first case. If we just had a Hertzian dipole, again with these side lobes, and then we had this group pattern here. It's basically just you multiply one times the other. So when you do, you see there's a null here and up and down, and there's a null to each side. So our resultant pattern, we'd expect nulls up and down and nulls to each side. And so we get this butterfly looking pattern. Another way you could do it is if you did have an isometric, that is projecting in all directions, and you did it times this guy, then you'd get exactly the same thing, right? Because this one's represented everywhere, so the only thing that affects it is the group pattern. So on the page for this class, I created a spreadsheet that you can play with if you'd like. It might even help you do some of the homework. And when you look at it, there will be 3 tabs. There's one tab on the bottom called unit pattern. The next one's going to be called group pattern, and the third one's resultant pattern. And so when you look at the top of each sheet, you'll see some green boxes, and those are the fields that you're allowed to change. So you can make it lambda over 2 or pi over 2 or whatever you want. And so you can create your own unit pattern. Then you can create, and vary your different group patterns. And then you can go to the third tab and see what the resultant pattern is. So feel free to download that and play with it like you want, or modify it, or do whatever you want. And like I said, that probably can help you with a couple of the homework problems. So you might want to play with it and get a feel for that a little bit and see how you can vary those patterns. So we can also apply the superposition principles to determine the pattern for more than 2 antennas. And again, this is very common, to use multiple antennas to get all kind of directivity that we want. We can even vary the directivity because you can vary the phase of the sources in real time. And so when you might hear of something called a phased array antenna. The military uses this a lot, and so they can sweep in a certain direction, and for using radar to determine the locations. And what they're doing is you don't see the antennas move, but they'll be varying the phase to each antenna, so it creates different patterns, and it's really kind of cool. So the quick example we're going to look at is if you had 4 antennas that were lambda over 2 apart. Well, the way we could look at this then is we know what 2 antennas are lambda over 2 apart. And so that we could superposition that and replace it with the new single antenna with this new group pattern. Same thing here. We would have 2 lambda over 2 apart, put them here. And so when we have these two resultants, it'd be the same as having those two lambda apart. So again, you can just keep applying those principles and coming up with things. And so in this case, you would have the first one, which was lambda over 2 apart, and so then be multiplied times these two guys at lambda apart, and this would be your resultant. So you can see this is actually pretty interesting because this antenna is not overly directive. That is, if I was trying to hit just a receiver out here at this point, you still have a lot of lost radiation not in that direction. Well, here I can actually narrow that lobe up and transmit more in the direction that I'm interested in. So that's a principle that's used in that sometimes. So again, download the spreadsheet, play with that a little bit, look at the homework, and hopefully you'll find this interesting.